So we're calling this chapter 4A, about naming compounds. And again, this is just the first part of chapter 4. And after this part, we're actually going to put chapter 4 away for a couple of weeks. And we're going to go on to more stuff that's oriented toward calculation and stuff that you're going to be using in the lab. So we're actually going to skip chapters 4, 5, and 6 after this and go into chapters 7 and 8, which are all about chemical reactions, balancing equations, and doing calculations with those material. But today we're focusing on naming compounds. And what we need to recognize and understand is that there are basically 3 types of compounds that we're going to name in this class. The first are ionic compounds. Ionic compounds are compounds that are made out of charged particles. And so when it comes to charged particles, we talked about them a little bit in chapter 2. There are the cations, which have a positive charge, and there are anions that have a negative charge. And we know now, based on some of our talk from chapter 2, chapter 3, that electron transfer is the reason for their charge. Now that we have an understanding of electron configurations, we can get a good idea of why calcium forms a positive 2 ion instead of a positive 1 or a positive 3 or a negative 5. So cations, they are positively charged because they give their electrons away. Anions are negatively charged because they take electrons in. And generally speaking, we are going to have a range of charges as follows. If it is negatively charged, it's going to be anywhere between -3 and -1, largely depending upon what kind of ion it is, how it's put together. If it's monatomic, that charge is going to be based on its position on the periodic table. If it's polyatomic, it's actually going to be kind of the same thing, but for a completely different reason. Cations generally range from +1 to +4. Most of them are going to be in the +2 and +3 range, at least as far as transition metals go. Again, periodic table has a lot to do with what's going to happen. So let's review some of the common charges here. Our alkali metals, the group 1s, all have +1 charges because, again, if we go back to the electron configuration, that valence electron configuration is something S1. So to get to a noble gas configuration, all of those metals ditch that S1 electron and go back to that noble gas configuration. Since they only ditch 1 electron, it's a +1 charge. Your alkaline earths, +2 charge, kind of the same reasons, based on its electron configuration. Group 13, same reason. Vacating that outermost energy level means it's going to have to get rid of 3 electrons. Getting rid of 3 electrons gives us a +3 charge. For our nonmetals and our metalloids, group 15, the nitrogen group, -3 charges on those. Group 16, the oxygen group, -2 charges on those. Group 17, the halogens, all of those are -1s. Now, again, this is for monatomic elements. So that is, we're talking about ions that have just 1 atom, and that atom's charge is based completely on where it is on the periodic table. Now, how do we recognize an ionic compound? Well, generally, we're looking for something that has a metallic component and a non-metallic component both at the same time. Now, because we are dealing with charged particles, we have to deal with something called charge neutrality. Charge neutrality means that we have to have an equal positive and negative charge. So when we're writing chemical formulas for ionic compounds, that's something that we have to consider. We have to make sure that all the positive charge is negated by negative charge, and vice versa. There can't be any leftover positive or negative charge. If we have leftover charge, then we don't have an ionic compound. We have an ion still. Now, the way that we can take care of this charge neutrality issue is something called the crisscross method. What the crisscross method states is that if I have two ions with differing charges, then all I need to do is the charge, the magnitude of the charge on the cation crosses over and becomes the subscript of the anion. And the magnitude of the charge on the anion crosses over and becomes the subscript of the cation. In mathematical terms, you can kind of think about this as, how do you find the lowest common multiple of two numbers? Well, the easiest way to do it is you usually multiply the two by each other, and that's usually the lowest common multiple between them. Sometimes you have to divide by 2 afterwards, but if you want a starting place for where to guess, that's usually what you do. And that's all that you're being asked to do here as well. We're basically finding the lowest common multiple of charge. And so we're going to crisscross the charges there. Now, this only works if we have charges that are different. If the charges are the same, then it's just a 1-to-1 ratio of the two ions. So if it's +2 and -2, the formula is not Mg2O2. It reduces down, it's MgO. If the charges match, you just push the two ions together and you take away the charges. It's a 1-to-1 ratio. So as we start to look at these three main groups of compounds, we've already talked a little bit about ionic compounds and how to recognize them. The other two kinds of compounds are covalent compounds. So what we have here are, we already discussed, we've got ions, usually between a metal and a nonmetal. Covalent compounds are almost always nonmetals with each other. And then acids are kind of weird. Acids are covalent compounds. But when we put them in ion, or when we put them in water, they will ionize. So they kind of have their foot in both doors. Most often we will see acids as looking like covalent compounds, a cluster of non-metallic substances put together. But because acids are hydrogen and something else, the fact that that hydrogen has a +1 charge, and the fact that the bonds that are usually made are quite polar, water splits them apart, and we end up getting hydrogen ion and some other ion in water when it goes into water. Now, because they are all different kinds of substances, they all have different naming systems. So again, we'll start with the ionic compounds. We can recognize an ionic compound as having either a metallic and non-metallic component. So sodium and sulfur, beryllium and chlorine, aluminum and oxygen, or this is where that knowledge of the polyatomic ions comes in. We recognize that the formula has a polyatomic ion in it, and if it has a polyatomic ion in it, it is either an ionic compound, or if it's paired with hydrogen, it's an acid. Now, as far as naming system is concerned, the naming system here is really easy. We just have to identify the cation and the anion, the positively charged substance and the negatively charged substance. And we write down their names in that order. Cation first, anion last. So because of this naming system, we just have to be able to recognize what the ions are. If we can recognize ions by their formula, then it just becomes a matter of putting the names in the correct order. And if we have to flip it around and turn names into formulas or formulas into names, then we recognize that the formula has the same way of putting itself together. The cations first, the anions last. So cations. Normally, cations are metallic elements. The one exception to that rule is the ammonium ion, NH4 positive 1. That is the only polyatomic ion that we have on our list that has a positive charge. Now, if we were looking at the ion by itself, that is outside of a polyatomic, or excuse me, outside of a compound, if I just had NH4 plus listed, I would name that as ammonium ion. Ammonium for the NH4 cluster, ion because it has a charge. I would put both of them in that description, because without that, it implies that it is uncharged. If I don't say ion at the end, it implies that there's no charge on that cluster. So the same thing for all these. Sodium ion, Na+1. Barium ion, Ba+2. As we saw at the end of chapter 3, transition metals can be a little bit tricky. Transition metals have the possibility for multiple charges because, as we saw, that D organization, that D sublevel, has multiple ways of being stable. And so because there are multiple types of ions of those transition metals, we have to have a way of telling them apart. And that's where our Roman numeral system is going to come in. The Roman numerals tell us the charge on the ion. And that's important to note. The Roman numeral does not give us the subscript in the chemical formula. It gives us the charge on the ion. So lead, for example. We know lead as either being +2 in charge or +4 in charge. So it can either look like this or it can look like this. Using Roman numerals, we would differentiate between the two. This one would be lead 2+, so this is the lead 2 ion. This one, lead 4+, that's the lead 4 ion. Anions, on the other hand, not quite as complicated because there's no transition metals to worry about. Where they're talking about something that is non-metallic, or we're talking about one of those polyatomic ions that we asked you to memorize. Now, for the ones that are non-metallic, the ones that we pull off the periodic table, we are going to adjust their names slightly to convey that they have a negative charge. So that's what this is talking about right here. We change the ending from whatever it is to IDE to signify that it is an ion and that it has a negative charge. So sulfur would become sulfide. Oxygen becomes oxide. Nitrogen becomes nitride. Chlorine becomes chloride. It's a subtle change. But again, it's one that makes sure that we know exactly what we are talking about. And it also helps us to tell apart these kinds of ions from other ions that are polyatomic that sound similar. So sulfur, for example, from your polyatomic ion sheet, you know that there is such a thing as sulfide, S-2. There is also sulfate, SO4 -2. There is sulfite, SO3 -2. There's hydrogen sulfate, H, SO4 -1. And there's hydrogen sulfite, H, SO3 -2, -1. That ending there, IDE, helps us to differentiate. This is the monatomic versus the polyatomic. Notice that all of your polyatomic ions, with the exception of cyanide, end with either ATE or ITE as their suffix. Because that ending signifies that there is oxygen in that ion somewhere. That's why cyanide doesn't end in ATE or ITE, because it doesn't have oxygen in it. The one that does have oxygen in it, cyanate, looks exactly the same as cyanide, but with an added oxygen. So we can look at a couple of examples. Let's say that we have these compounds. I've got MgCl2. Well, I can look at the formula here and recognize, okay, this is just magnesium. So the cation's name is magnesium ion. Cl is just a monatomic ion. So we got to change chlorine to chloride. So that's where we get chloride ion here. Put the two together and it's magnesium chloride. Notice that when we go from the ion name to the compound name, we drop that ion ending because it's no longer charged. I can look at K2S. K2S, I recognize, okay, K is potassium, S is sulfur. So the cation here would be the potassium ion. S, sulfur. Well, I got to change the ending. Sulfur turns into sulfide. So the anion here is sulfide ion. Put the two together, it's potassium sulfide. If we start to throw in polyatomic ions, it just becomes a recognition of those ions. NH4, I have to recognize that that's the ammonium ion. So NH4Cl, I've got the ammonium ion, I've got the chloride ion. The compound's name is ammonium chloride. For FeOH taken 3 times, I've got to recognize 2 things here. First of all, I need to recognize that iron is a transition metal. Transition metals are going to have variable charges, and so I'm going to have to put a Roman numeral on it. And so that's your general rule of thumb. If it is a transition metal, it's going to have one of these Roman numerals on it. The only ones that don't are in that triangle that I've mentioned maybe once before. In the transition metals, you've got zinc, silver, cadmium, and indium. Right at the very end of that S block, or excuse me, that D block. That triangle of substances has no variability. So for zinc, silver, cadmium, indium, you don't need to put in a Roman numeral. They are only going to carry a +1, +2, or +3 charge. It's the only charge that they have. And so since it's the only charge that they have, Roman numeral is not only unnecessary, it's actually incorrect. The reason it's incorrect is because by putting a Roman numeral on there, it presupposes that there's another form, another ion that is possible for that element. Zinc can only be +2. There is no other form of it. So the Roman numeral is not necessary. It's not correct. Because there is no zinc 1 or zinc 3 to compare it against. 2 is the only correct form. So we have to recognize that the iron here is a variable charge. How do we get iron 3? Well, we have to recognize that the other substance here, the hydroxide, is a -1 charge. Since it is a -1 charge and there are 3 of them, the iron has to be +3 to match. So we can almost think of that as the opposite crisscross. So the crisscross rule works in both directions. I can use the charges as I know them to give me the chemical formula. I can also use the chemical formula to switch it back and give me the charges if I don't know them. So I've got the iron 3 ion, I've got the hydroxide ion, I put them together. The correct name for that compound is iron 3 hydroxide. Okay, so that's ionic nomenclature. Now, when it comes to covalent nomenclature, again, we're talking about substances that are sharing electrons, so there are no charges here. What we will find is that even though the way that the molecules are put together is different, the naming structure is very similar. But since we don't have charges and the crisscross rule to help us explain why the subscripts are the way that they are, we have to account for that numbering in our naming. And what that means is we have to become familiar with prefixes, numerical prefixes. So most of these prefixes are prefixes you've actually heard before, even if it's been a while. Most of these are geometric prefixes. So if I'm describing a five-sided object, I would call it a pentagon. Penta being the prefix that means five. So these prefixes are somewhat familiar to you, but with some notable exceptions. First of all, prefix for one is rarely used outside of very specific circumstances. It's mono. Prefix for two, instead of bi, which is what the geometric term would be, like bisecting a line, riding a bicycle, we use the prefix di in this context. For three, it's tri, pretty familiar. For four, it's tetra. Tetra will become much more useful to us. We'll find ourselves using it a lot more when we talk about molecular shapes in chapter 5. 5, penta. 6, hexa, relatively straightforward. 7, hepta instead of septa. 8, octa, again, familiar. 9, nona. 10, deca. So with a few exceptions, we've heard most of these prefixes before in different contexts. Now we're just bringing them into a chemical context. How do we use these prefixes to ultimately help us determine what the name of a compound is? Well, this is where the structure is very similar to ionic compounds. We go in order. First element first, second element second. First element, we attach a prefix to it, unless there's only one. If I only have one of that first element, we assume one is implied and we don't put a prefix on it. To the second element, we do the same thing. Prefix on the front, but we also add that IDE suffix on the end. So again, very similar to what we saw for the for the ionic compounds for the anions. IDE ending, but we're also adding a prefix on it as well. And then we just put the two names together. So it's prefix element IDE. That's how we name a covalent compound. And these are all going to be non-metals. Because again, that's the only thing that does covalent bonding is non-metals. So we can take a look at a couple of examples here. So CO2, we start with the first element, carbon. Since there is only one carbon, mono is implied. We do not need to call it monocarbon. It's just carbon. Second element, dioxide. Prefix di, 2, oxygen, IDE, dioxide. Put the two together, CO2 is called carbon dioxide. Now you already knew that, but now you know why that is its name. Let's look at the other one. S3Cl8. Okay, well, I start with the first element, sulfur. There are 3 sulfurs, so this is going to be trisulfur. Chlorine is the second element, Cl. There are 8 of them. I have to change the ending. Octa for 8. Chlor for chlorine, ide because it's the second element, octachloride. Put them together, S3Cl8, trisulfur octachloride. And that's all that we have to do. That's all that covalent naming is just breaking it down into first element, second element, prefixes. Now the last one, acids. Acids we can identify in a couple of ways. One way that we can do it is by looking at, okay, it appears to be ionic. So it's got a polyatomic ion on it. But the cation is hydrogen. If we consider hydrogen as a +1 ion, all of these look like ionic compounds. So even though hydrogen is non-metallic, its +1 characteristic is going to make this feel a little more ionic than it actually is. Now, the other way we can do it is just simply looking at the formula. If a formula starts with hydrogen, chances are really good it's an acid. The only exception really there is water. Aside from water, the compound name, if the compound formula starts with hydrogen, you're probably looking at an acid. Now, as far as acid naming goes, there are two different types, and unfortunately, those two different types have two different naming systems. The first is called a binary acid. Binary acids we can identify as simply acids that have hydrogen and one other atom. These tend to be the ones that we think of the most when we think of acids. Hydrochloric, hydrobromic, hydroiodic. What's interesting about these compounds is that they actually do exist outside of water in the gas phase. And so one of the things that we have to be really careful about when we look at those compounds is looking at what phase of matter they are. They're in the gas phase. They're not technically acids yet. We would name them as ionic compounds because of it. So HCl in the gas phase is hydrogen chloride. HCl in water, aqueous, hydrochloric acid. Ternary acids, on the other hand, we usually can pick them out because there's a polyatomic ion attached to the hydrogen. Now, the one exception to the rule here, hydrogen cyanide, HCN. HCN is actually named like a binary acid. And the reason why it's named like a binary acid is because unlike all the other acids that have oxygen in them and get named according to their oxygen characteristic, it doesn't have oxygen. So it's going to get named like all the binary acids do. Now for binary acids, we have a very strict formula that we follow. It's hydro blank ic acid. What goes in that blank is basically the root of whatever it is that's attached to the hydrogen. So if it's chlorine, hydrochloric acid. If it's bromine, hydrobromic acid. If it's cyanide, hydrocyanic acid. Whatever is attached to that hydrogen We just drop it in the blank. And again, if we don't see these aqueous signs here to indicate that it's in water, we name it like it's an ionic compound, because these are all gas phase substances outside of water as well. For the ternary acids, where we have a polyatomic oxygenated ion, it's a matter of changing the ending. So whatever the ion is, we are going to change the ending of that ion's name to one of the two on the board. And it all depends on what that substance is. So if I am dealing with an 8 ion, sulfate, phosphate, oxalate, acetate, the name of that ion just gets changed from whatever 8 to whatever ic acid. Sulfate becomes sulfuric acid. Phosphate becomes phosphoric acid. Cyanate becomes cyanic acid. Oxalate becomes oxalic acid. Now, for some of the ones in the middle there, phosphorus and sulfur in particular, notice that we had to change slightly our pronunciation. Instead of sulfic acid or phosphic acid, we added that UR, that OR in there. Phosphoric, sulfuric. That's mainly a stylistic thing. Makes it a little bit easier to say. If our ending is in ITE, like chlorite or hypochlorite, sulfite, it gets changed to us acid. So sulfite becomes sulfurous acid. Hypochlorite becomes hypochlorous acid. So if there's a prefix on the front, that prefix stays. All the hypos stay, they become hypo whatever ic acid. All the pers stay. Perchlorate here becomes perchloric acid. It just adds on.